Good morning. Today we'll be talking about the very important aspect of cyclonation reaction, something called rate of cyclonation reaction. In this topic we'll be discussing that how do the rate of a particular cyclonation reaction differ from the other, and we'll talk about the extent of the difference in the rates owing to the substitution patterns on either diene and dienophile. To understand this topic, we'll start by taking an example of a simple Diels-Alder cyclonation reaction, the reaction between a butadiene and an ethene. We know that in the case of butadiene, we have two double bonds, and the presence of the two double bonds, the two conjugated double bonds, make this system comparatively more stable than any other system which has an isolated double bond, for example an ethene. Therefore, overall, comparing the energies of the stabilities of, I can say, overall butadiene with two conjugated pi electron systems should be more stable than ethene. But once we talk about the entire energy or the entire molecule, we'd say butadiene is comparatively more stable as compared to the ethene. But once we talk about the valence orbitals, once we talk about the energy of the HOMO and the LUMO, it was found out that HOMO of butadiene or any diene, which is of course Cy2, which has of course one node, the value of this the energy of the HOMO in terms of the energy is somewhere around minus 9.1 electron volts, whereas that of HOMO of dienophile, which in this case of course is the ethene molecule, which of course is the pi 1 having 0 node, was calculated to be minus 10.51 electron volts. That would mean that HOMO of diene is having more energy than HOMO of dienophile, and conversely, and similarly LUMO of diene should have more energy than LUMO of dienophile. This would mean that we talk in terms of the total energy of the system and say butadiene is more stable because it has two conjugated pi bonds. But when we talk about the individual HOMOs and LUMOs in the case of butadiene and ethene, we say, and it has been calculated from photoelectron spectroscopy, that the energies of HOMO of the diene and that of the dienophile was calculated to be minus 9.1 electron volts and minus 10.51 electron volts. Therefore, the HOMO of the diene is at higher level of energy as compared to the HOMO of the dienophile, and similarly LUMO of the diene would be comparatively at a high energy level as compared to the HOMO of the dienophile. Therefore, while comparing the HOMO-LUMO interactions in the case of diene and dienophile, we can say that the energy gap between the HOMO of the diene and the LUMO of the dienophile, since HOMO of the diene is higher placed as compared to the HOMO of the dienophile, the energy gap between the HOMO of the diene and that of the LUMO of the dienophile is smaller as compared to the energy gap between the HOMO of the dienophile and LUMO of diene. If you understand this thing, this would mean that HOMO of diene and LUMO of dienophile are far closer in energy as compared to the HOMO of the dienophile and LUMO of the diene. This would mean the extent of perturbation which HOMO of the diene and LUMO of the dienophile will undergo, and obviously the extent of stabilization which they will produce would be comparatively larger in terms of energy values as compared to the HOMO of the dienophile with the LUMO of the diene. This would mean that even though both interactions, HOMO of diene with LUMO of dienophile or HOMO of the dienophile with LUMO of the diene is stabilizing the molecule in terms of the energy values, but the extent of stabilization is different. This we have talked earlier also. The stabilization delivered by the HOMO of diene with LUMO of the dienophile is far larger as compared to the stabilization which is achieved when we consider the perturbation or interaction between the HOMO of the dienophile with LUMO of the diene. This would mean that it is HOMO of the diene and LUMO of the dienophile's energy interaction which should be more considerate, more contributing to the energy of the molecule then the HOMO of the Diophyte, the LUMO of the diene. To substantiate this point and talk about this thing further, we talk about something called the effect of substituting, groups on the nucleus of diene or Diophyte, or you can for that matter say on any polyene system. What will be the effect? Let me show this diagrammatically and then try to explain this thing. Let me draw the energy axis here. This is the energy axis. Let's say this is the zero of the energy. This is the energy axis. This is the zero of the energy. Right? This is, let's say, the HOMO of a particular alkene. Let's say we are talking about ethene in this, for example, only. Let's say this is the HOMO of ethene. This one is HOMOs all the way. And of course, this one is LUMO all the way, let's say. And this is the bonding molecular orbital. This one is the anti-bonding molecular orbital. If I substitute this system, which is a single electron, let's say this is ethene molecule only, for example, ethene only. If we substitute ethene with, let's say, an electron donating group, what would happen to the energy levels of these orbitals, the HOMO and the LUMO, once this molecule is substituted by an electron donating group? To understand this topic, let's say what effect the electron donating group will have on a pi bonded system. Since we are talking about a pi bond, we are talking about the two molecular orbitals corresponding to a pi bond. Once we substitute this kind of a system with an electron donating group, an electron donating group will tend to give electrons to the pi electron system. That pi electron system, which is already electron rich, because of the donation of the pi electrons from the electron donating group, will tend to become more electron rich. And if it is more electron rich, there will be more interelectronic repulsions, as the result of which the energy level of these kind of systems energy levels of this kind of system would get raised higher in energy as compared to the parent system. So what I'm trying to say is, once substituted by electron donating group, the energy levels of the HOMO will go somewhere higher and will come here, where D represents the substitution by an electron donating group. Similarly, the LUMO will be raised in energy. Well, this is hypothetical because normally speaking, under thermal conditions, the LUMOs are vacant. And since they are vacant, we cannot consider this as LUMO. Even for photochemical systems also, LUMOs are vacant. So substitution of the electron donor or electron acceptor group on a vacant system does not make any sense. Anyways, just for the sake of writing, the same effect whatever a HOMO will have on the substitution of electron donating group, the same effect the LUMO will have on the substitution of electron donating group. That means both the electronic levels or both the orbitals will rise in energy level, rise in terms of energy once substituted by the donating group. And the reason for this is simple again. Once the electron donating group is substituted, the electron count or the interelectronic repulsions of that particular alkene system increases, which makes them comparatively less stable and hence raises high in energy. And correspondingly or conversely, once we have any system which can probably remove the interelectronic repulsions in this system, would probably stabilize it, and that is the effect which an electron accepting group gives. So if I'm substituting a system with an electron accepting group, it takes away some electrons from this pi electron system, makes it comparatively, there will be comparatively less interelectronic repulsions, and as the result, this system would comparatively be much stable and therefore will go lower in energy. Whatever is the effect of HOMO, the same would be effect on the LUMO as well. Therefore, we can see two things where D is a electron donating group and of course A is the electron accepting group. Therefore, we are witnessing two things. The first thing we are witnessing is that once you substitute a normal system, a normal alkene system, whether it is a ethene, a butadiene, a hexadiene, or any polyene system, the effect on the HOMOs and LUMOs are very, very clear. Once it is substituted by an electron donor group, the HOMOs and the LUMOs tend to raise higher in energy. And if we tend to substitute it with an electron accepting group, which takes away the electrons and reduces the interelectronic repulsions, the HOMOs and LUMOs are lowered in terms of the energy. Now, once this effect is done, definitely since the energy levels have changed, and the extent of energy level change will have an effect on definitely on the the extent of the interaction between HOMO of one reactant and LUMO of the other reactant, and this can alter the speed of the reaction as well. Therefore, in general, if we talk about this thing, that HOMO of the diene is at higher energy than the HOMO of the dienophile. If this is the case, we call these cycloadditions as Diels-Alder cyclonation reactions as normal. The word normal is used. Normal Diels-Alder cyclonation reactions. Hence, whenever we use this word normal Diels-Alder cyclonation reactions, this would mean that the HOMO of the diene is always higher in energy than the HOMO of the dienophile. Now, let's say if we are considering this normal Diels-Alder cyclonation reactions, let's take and explain the extent of interaction between the HOMO of the diene and dienophile, and conversely the interaction between the HOMO of the dienophile with the LUMO of the dienophile with the diene. We're talking about normal Diels-Alder reaction, which would mean HOMO of the diene is higher in energy than HOMO of the dienophile, which we have been repeatedly saying. Okay, we have a diene here, we have a dienophile here. We are trying to draw the molecular orbital picture of this thing. Let's try to draw the molecular orbitals of diene and dienophile. As we know, diene is a 4-electron system, therefore there will be 4 molecular orbitals: Psi1, Psi2, Psi3 star and Psi4 star. Psi2 will have 2 electrons and would be the HOMO. Psi1 would be the lowest energy orbital in terms of the filled orbitals. Similarly, dienophile is a 2-electron system, 2 molecular orbitals, Pi1 and Pi2 star. HOMO would be Pi1 and LUMO would be Pi2 star. And since it's a normal Diels-Alder reaction, I have to depict it in such a way that HOMO of the diene is higher in energy than HOMO of the dienophile. So while drawing this molecular orbital level diagram, what I'm trying to show is that in terms of energy, HOMO of the diene is higher in energy than HOMO of the dienophile. Look at the energy gap. We've tried to keep this higher energy, and we have to try to keep this lower energy. And similarly, LUMO of the diene is higher energy than LUMO of the dienophile. Now, the extent of stabilization, we've said this thing that you can take any HOMO-LUMO interaction in the FMO approach. You take HOMO of the diene and LUMO of the dienophile. This would have the similar result in the terms of reaction conditions. And in terms of reaction conditions, if you take HOMO of the dienophile and LUMO of the diene, it will have the same results. However, since the energy gap between HOMO of the diene, as depicted in this case, and LUMO of the dienophile is less, you see, this HOMO is higher energy than HOMO of the dienophile. This LUMO of the dienophile is lower energy than LUMO of the dienophile. So if you look at the energy gap, this is less, this energy gap is large. So it is the energy gap, the extent of the smaller is the energy gap between the two interacting molecular orbitals. More will be the interaction or the perturbation between them, more will be the stabilization, and more will be the destabilization. I'll repeat what I'm saying. Smaller is the energy gap between the two interacting orbitals, which in this case, let's say, is HOMO of the diene and LUMO of the dienophile. If the energy gap is small, the extent of interaction or perturbation is also high, and since it is high, the extent of stabilization and extent of destabilization will always be higher. That would mean if the two atomic orbitals are interacting, two molecular orbitals will be formed, one which is bonding, let's say I'll call this as Psi1, and the one will be bonding, let me call this as Psi1 star. Now, in terms of the stabilization, Psi1 would be stabilized to a larger extent and Psi1 star would be destabilized to a larger extent. But luckily, while interacting a HOMO and the LUMO, we have to only combine 2 electrons, so only Psi1 will be filled. Psi1 star, since is empty, has no contribution in terms of energy. Therefore, if Psi1 is lowered much in energy, that means the extent of stabilization provided by this interaction is larger, higher, and therefore this interaction is more contributing to the system. Conversely, if you look at the interaction between the HOMO of the dienophile with LUMO of the diene, we're trying to say that the energy gap is large. Since the energy gap is large, the extent of interaction or perturbation would be small. That would mean the extent of destabilization and stabilization provided by such interaction would be less. Therefore, if these two atomic orbitals are combining, let's say 2 molecular orbitals are being formed. We call this as Psi2 and Psi2 star. Again, since I have to combine 2 electrons will go to Psi2, no electrons will be there in Psi2 star, therefore this does not contribute in terms of energy. The extent of stabilization is small. The extent of stabilization in the case of HOMO diene and LUMO dienophile is large. Therefore, E1 is far higher in terms of energy than as compared to E2. if E1 is far higher in terms of energy as compared to E2, which would mean the extent of stabilization provided by the interaction between the HOMO of the diene and LUMO of the dienophile in terms of a normal Diels-Alder reaction is larger. Therefore, it is this interaction which is actually contributing to the stability of the system more, and it is this interaction which should be our consideration while discussing the rates of cyclonation reactions as well. Therefore, if I repeat these things again, as evident, the HOMO-LUMO gap in HOMO-diene and LUMO-dienophile is small, extent of perturbation or interaction is high, and the corresponding lowering of energy level E1 is more. Conversely, HOMO of the dienophile with LUMO of the diene energy gap is large, extent of stabilization is less, and therefore the value of E2 is smaller. Hence E1, the extent of stabilization while considering the HOMO of the diene with LUMO of the dienophile is much higher, and E2 while considering the HOMO of the dienophile and LUMO of the diene is smaller. Therefore, our consideration would always remain the interaction between the HOMO of the diene and LUMO of the dienophile while considering a normal Diels-Alder cyclonation reaction. Therefore, we can now say, considering this molecular orbital energy level system, that more contribution to the stability and hence more important interaction is HOMO of the diene with LUMO of the dienophile. Less important interaction is HOMO of the dienophile with LUMO of the diene. That's why I've not written here. Hence, any substitution on these two molecular orbitals, that is HOMO of the diene with LUMO of the dienophile, would actually control the reactivity, the speed of the cyclonation reactions. Let's take an example to explain what do we mean by explaining this thing that the HOMO of the diene and LUMO of the dienophile are more important interactions, and it is the substitution pattern on these systems which will control the overall speed of the reaction. Let's take an example where we compare the reactivity of a Diels-Alder cyclonation reaction between a butadiene and an ethene with or without the substitution of a nitrile group, a cyano group. So I have two reactants, a diene and a dienophile. Let me write, since I'm doing nothing on a dienophile, so I'm writing just two molecular orbitals for dienophile. Now this is, forget about this and this orbital for a moment. Let's say I have these two orbitals only, this one and this one, a diene and a dienophile, right? Now, of course, as drawn in this molecular orbital energy level diagram, the HOMO of the diene is drawn at higher energy level than the HOMO of the diene is drawn at higher energy level than the HOMO of the dienophile. Therefore, I'm depicting a normal Diels-Alder cyclonation reaction. Right? Now, the interaction of HOMO of the diene and LUMO of the dienophile, as I've told you, is more contributing. Therefore, I'm studying this interaction. So, once these two interact, there will be an extent of stabilization corresponding to the value E1. Right? So this, and of course, as you know, that once if it stabilizes, it destabilizes the antibonding orbital also, and since no electrons are to be accumulated here, therefore the energy considerations corresponding to the destabilization are not discussable here. Hence, we talk about the HOMO of the diene and LUMO of the dienophile with a stabilization E1, which is provided by this kind of an interaction. Now, the point is, if you substitute the diene with a nitrile group, nitrile iodocyano group is an electron withdrawing and accepting group, both in terms of resonance as well as in terms of the inductive effect. Therefore, once it pulls the electrons, withdraws the electron, it stabilizes the HOMO of the diene and brings it at a new energy level which is lower in energy as compared to this one. So once a diene is substituted by a nitrile group, it tends to get lower in energy by a factor. And similarly, if the LUMO is substituted, because the molecule as whole has to be substituted by a substituent, therefore if HOMO is affected, similarly we can depict the extent of the LUMO's stability. So HOMO is stabilized for the diene, LUMO is also stabilized for the diene. But this kind of a stability, what does it do to the extent of interaction between the HOMO of the diene and LUMO of the dienophile, which is more important to me. Once the HOMO of the diene is lowered in energy, that means the gap between the HOMO of the diene and LUMO of the dienophile has increased. Earlier, when it was higher in energy, the gap was smaller. Once it has become lower in energy by the substitution of an electron withdrawing or an accepting group, the gap has intensified. It has increased, and since the gap has increased, the extent of stabilization or the extent of interaction would be less. The extent of stabilization would be less, and hence I can say the reaction would occur comparatively slowly as compared to when there was no substitution in the diene. And since, of course, as I've depicted, the extent of stabilization provided when there was no substitution is E1, the extent of stabilization provided when there is a cyno or an electron accepting group is smaller, that is E2 as compared to E1. E1 is much higher in terms of energy as compared to E2. Therefore, substituting a nitrile group onto the nucleus of diene increases the energy gap between the HOMO of the diene and LUMO of the dienophile, decreases the stability of the system by a factor E2, which is smaller as compared to E1, and hence the reaction speed also retards and becomes slow in nature. Hence, we can predict that if I substitute a nitrile group or any electron accepting group onto a diene in a normal Diels-Alder cyclonation reaction, it would definitely lower the energy or lower the speed of the reaction. So this kind of a result can be generalized for all substitutions, all electron accepting substitutions on diene. Whenever you substitute an electron accepting group on a diene, the HOMO tends to be lower in energy. This increases the energy gap, lowers the interaction, lowers the stability, and decreases the speed of the cyclonation reaction. Let's take another example in which we want to compare the reactivity of a particular Diels-Alder cyclonation reaction when we substitute an electron withdrawing or an accepting group onto the nucleus of a dienophile. Let's say, for example, if we are considering a DA cyclonation reaction between a simple butadiene and a nitroethene, let's say, where a nitro group is substituted to the ethene moiety, that is the dienophile. Now, we know that this is a normal Diels-Alder cyclonation reaction in which the more important interaction energetically as well as reactivity speaking is the HOMO of the diene with the LUMO of the dienophile. And if an electron accepting group nitro is substituted onto dienophile, that would mean that it will lower the energy of both the HOMO and LUMO of the dienophile. We're not talking about diene here, we're talking about the dienophile here. That means the HOMO and LUMO of the dienophile will be lower in energy. This would mean that the energy gap between the HOMO of the diene and LUMO of the dienophile will reduce. And once the energy gap reduces, the extent of perturbation and interaction increases. As the result, the stability increases and therefore the reaction should speed up. In terms of molecular orbital energy level diagram, let's try to draw this thing. We're talking about diene on the left side, dienophile on the right side. Let's try to understand this thing using this picture. I'm only drawing the HOMO and LUMO for the diene, and for a moment, forget about this thing, forget about this one, that there are no orbitals here. Then first of all, we talk about the HOMO of the diene with the LUMO of the dienophile, which is not substituted. Of course, HOMO-LUMO interaction brings about a stability by the factor of, let's say, E1. Once you substitute dienophile with an electron withdrawing nitro group, what will happen? It will lower in energy both the LUMO as well as the HOMO. Now because in the normal Diels-Alder reaction, we are considering the interaction between the HOMO of the dienophile with the new LUMO of the dienophile, which is now lower in energy. Now that means what a substitution has done on dienophile is it has lowered its energy, and once it has lowered its energy, the energy gap between the HOMO of the diene and LUMO of the new dienophile, which is substituted with the nitro gap, is now less. And since the energy gap is less, the interaction would be more, the perturbation would be more, and extent of stability would be more. Therefore, as drawn diagrammatically, the extent of interaction between HOMO of the dienophile with LUMO of an electron accepting group substituted dienophile is more. Therefore, it is lowered much in energy. Hence, I am showing here that E2 is larger than E1. This would mean that substituting a nitro group onto the nucleus of dienophile lowers the HOMO-LUMO energy gap, increases the stability of the reaction, and therefore increases the speeds of a Diels-Alder cyclonation reaction. Hence, we can say, if we are considering normal Diels-Alder reaction, electron accepting substitution slows the reaction, whereas electron accepting substitution on the dienophile speeds up the reaction. Similarly, if we substitute an electron donating group onto the nucleus of, let's say, this should be diene, onto the nucleus of a diene, let's say, if we substitute electron donating group onto the nucleus of the diene, what will it do? It will raise its level, increase the energy level of the HOMO of the diene, and as the result of it, since in the normal Diels-Alder reaction, it is the HOMO of the diene and LUMO of the dienophile which is more contributing. Since the HOMO is raised up in energy, the energy gap between the HOMO and LUMO is now reduced, and if the energy gap is reduced between the HOMO of the diene and LUMO of the dienophile, this speeds up the reaction. Therefore, substituting an electron donating group on diene speeds up the normal Diels-Alder cyclonation reaction, and conversely, if you substitute the electron donating group onto the nucleus of a dienophile, what will it do? It will raise the orbital, it will raise the LUMO of the dienophile, and as the result, the energy gap between the HOMO of the diene and LUMO of the dienophile increases. And since the energy gap increases, the reaction, the perturbation or the interaction also decreases. As the result, the reaction tends to slow down. Therefore, I can say simply that normally speaking, if I want to have a fast Diels-Alder cyclonation reaction, I need to reduce the energy gap between the HOMO of the diene and LUMO of the dienophile. That's the only thing. Energy gap between the HOMO of the diene and LUMO of the dienophile can be reduced if I raise the HOMO up and if I lower the LUMO down. Now, to raise the HOMO up would mean I need to substitute the diene with an electron donating group, and to lower the LUMO of the dienophile would mean I need to substitute the dienophile with the electron withdrawing or electron accepting group. Therefore, in order to have a fast Diels-Alder cyclonation reaction, diene should be substituted by an electron donating group and dienophile should be substituted by an electron withdrawing group. So that is how we can work out the effect of substitution onto the nucleus of diene and dienophile in a normal Diels-Alder cyclonation reaction. Now we've been using this word normal Diels-Alder cyclonation reactions. Now let's talk about what are the other types of Diels-Alder cyclonation reactions which are possible. Now we classify the DA cyclonation reactions on the basis of the energy positioning of the HOMO and LUMO of diene and dienophile. So therefore, on the basis of energies of HOMO and LUMO of the diene and dienophile, DA cycloadditions are largely categorized into three subtypes. Type 1, which is called the normal Diels-Alder cycloaddition reaction, which we've already discussed, is the one in which HOMO of the diene is higher in energy than the HOMO of the dienophile, and as the result, the HOMO of the diene and LUMO of the dienophile is a significant interaction. HOMO of the dienophile and LUMO of the diene is a less significant interaction. Therefore, and similarly, I can say if it is HOMO of the diene and LUMO of the dienophile, HOMO of the diene is higher in energy than HOMO of the dienophile. Similarly, LUMO of the diene will be higher in energy than the LUMO of the dienophile. This is type 1. And in type 1, the major interaction is HOMO of the diene with the LUMO of dienophile. This is the major interaction onto which substitution pattern should matter. Type 2, the second category of Diels-Alder reaction. Well, this is a rare case, but it is a case in which both the HOMO and of the diene as well as the dienophile are placed at same energy levels. Similarly, if the LUMO of the diene and dienophile are placed at similar energy levels, then we say this is type 2 category. It is a rare case, but if that is the case, that HOMO of the diene and HOMO of the dienophile are at same energy level, LUMO of the diene and LUMO of the dienophile are at same energy levels, this would mean that the HOMO-LUMO interaction of either the diene of HOMO of diene with LUMO of dienophile or HOMO of the dienophile with LUMO of the diene would be equal, would have equal energy gaps, would be equally contributing. So both substitution patterns, so both the interactions are equally important, and substitution on both type of orbitals should affect the overall reactivity or the speed of the reaction. This is the second type of Diels-Alder cyclonation reaction. The third type of Diels-Alder reaction, which we use this word type 3, also known as inverse electron demand Diels-Alder cyclonation reaction. If type 1 was normal, type 3 is inverse electron demand. And when we use this word inverse electron demand, that means electron demand is opposite, inverse of what it was in the case of normal Diels-Alder. What do we mean by this? That would mean that HOMO of the diene is actually lower in energy than HOMO of the dienophile. This was the converse or the opposite case. Earlier in the case of normal Diels-Alder cyclonation reaction, we said that it is the HOMO of the diene which is higher in energy than the HOMO of the dienophile. In inverse Diels-Alder cyclonation reaction, it is the HOMO of the diene which is lower in energy than HOMO of the dienophile, and similarly LUMO of the diene should be lower in energy than the LUMO of the dienophile. So type 3 is exactly opposite to type 1, and hence in this particular case it is the HOMO of diene with LUMO of dienophile which is less contributing and is less important in interaction. On the contrary, it is the HOMO of dienophile and the LUMO of diene which is more contributing and is more important in interaction. And of course, as I've told you, in type 2 both interactions, that is HOMO of diene with LUMO of dienophile or HOMO of the dienophile with LUMO of diene, both are equally important. And here it was the HOMO of the diene and LUMO of the dienophile which was important in contributing. The other way around, that is HOMO of the dienophile in type 1 with LUMO of the diene is not an important interaction to be considered here. Therefore, having said or having demarcated the Diels-Alder reaction into three subtypes, namely type 1 called normal Diels-Alder reaction, type 2, and the last one, type 3, which is also called the inverse electron demand Diels-Alder cyclodation reaction, the energy levels of the HOMO of the dienes and dienophiles vary, and this is the basis on which these are categorized. Now let's try to draw and explain the same facts on the basis of the orbital picture. Let's try to work out this orbital picture. If you look at this orbital picture, we have drawn an energy axis, and by drawing the energy axis, you can see what we have tried to show. We've tried to show three different types of interactions: the type 1, the type 2 category, and the type 3 category. As you can see in the type 1 category, you can see this is diene and dienophile. Similarly, diene and dienophile for type 2. Similarly, diene and dienophile for type 3. And as I've told you, in the case of type 1, which is also called the normal Diels-Alder cyclodation reaction, HOMO of the diene, this is the diene side, HOMO of the diene is higher in energy than HOMO of the dienophile. Similarly, LUMO of diene is higher in energy than LUMO of the dienophile. Hence, the more contributing interaction is HOMO of the diene and LUMO of the dienophile because the energy gap is smaller. This is what we have shown by this solid line, and the dotted line represents that this interaction is less contributing and therefore less important. Hence, any substitution pattern on HOMO and LUMO of the diene and dienophile would affect the speed of the reaction. The second category was when HOMO of the diene is equal in energy. This was the energy axis. Let's say HOMO of the diene is equal in energy than the HOMO of the dienophile. Similarly, LUMO of the diene is equal in energy than LUMO of the dienophile. Since the energy gap between HOMO diene, LUMO dienophile and energy gap between HOMO dienophile and LUMO diene is same, therefore both the interactions are you can say the interactions are equally important, and since they are equally important, both would be contributing in nature, and hence any substitution pattern on either of the systems would definitely alter the speed of the reaction. And as I've told you, the type 3 category is the one in which is opposite to type 1. The HOMO of the diene is lower in energy than HOMO of the dienophile. Similarly, the LUMO of the diene is lower in energy than LUMO of the dienophile. And since now in this particular depiction one can find that HOMO of the dienophile and LUMO of diene's energy gap is less as compared to the energy gap between HOMO of the diene and LUMO of the dienophile. Therefore, it is the HOMO of the dienophile and LUMO of diene which is more contributing an interaction, and any substitution onto these orbitals would vary the speed of the reaction. Therefore, as I've told you, the contributing interactions are in the case of your type 1, HOMO of diene with LUMO of the dienophile. In the case of type 2, both are equally contributing, that is HOMO of diene with LUMO of dienophile or HOMO of dienophile with LUMO of the diene. And in the case of inverse electron demand Diels-Alder type 3 category, it is the HOMO of the dienophile and LUMO of the diene which is more contributing an interaction. Now let's see what kind of substitution patterns should speed up and slow down the reaction. In order to understand this concept, let's try to work out this table. I've divided this table into three parts. The first part or the first column is the type of cyclodation reactions. The second column is diene side. The third column is dienophile. Then the diene side is further divided into two columns: an electron donating group, electron withdrawing group substitution. And dienophile is also divided into two columns. One is electron donating and one is electron withdrawing group. Okay. In the case of type 1 cyclodation reaction, which is also called the normal cyclodation reaction, what will happen if you substitute the diene with an electron donating group? Now let's go back to this figure. This figure is a normal Diels-Alder cyclodation reaction where the HOMO of the diene and LUMO of the dienophile is a major interaction. Now if I substitute, as I've told you, if I substitute the diene with an electron donating group, what will happen? Electron donating group raises the level of the HOMO. As the result, if the HOMO has reached a new level, the HOMO-LUMO gap will decrease, and if the HOMO-LUMO gap decreases, there is an increasing interaction, increasing perturbation, which tends to speed up the chemical reaction. Hence, substituting a diene in a type 1 reaction with an electron donating group speeds up the reaction. And substituting a diene conversely with an electron withdrawing group, what does it do? If I substitute this diene here with an electron withdrawing group, I'm talking about type 1 normal Diels-Alder reaction. If I substitute this diene with an electron withdrawing group, this will lower the HOMO. Now HOMO will be lower than its actual position, hence the energy gap will increase. If the energy gap increases, the perturbation, the interaction will be less, and as the result, we can say that this particular reaction will be one, in which case you'd find that this particular reaction is one in which there is a slowdown in the energy. Therefore, I can say that for type 1 reaction, substitution, electron donating substitution on a diene speeds up, electron withdrawing substitution on the diene slows down. And conversely, if substitution patterns are to be studied on Diophyte in type 1 category, Diophyte here, electron donating group should raise it up, increase the energy level, slow down the reaction. Electron withdrawing group, lower its energy, lower the energy gap, speed the reaction. Therefore, a donating group should slow it down, whereas the electron withdrawing group should speed it up. This is the case in the case of type 1. Now let's look at the type 2 category. Let's see the results. In type 2 category, I substitute a diene with electron donating group, speeds up. I substitute a diene with electron withdrawing group, it speeds up. I substitute a Diophyte with electron withdrawing group or a donating group, the reaction speeds up. What does it mean? To understand this point, let's look at this figure here. Both energy levels are equally contributing. Let's say if I substitute a diene with an electron donating group, what will happen? If with the substitution of electron donating group, HOMO will be raised. Similarly, this LUMO will be raised. Once this HOMO is raised, this energy gap is lowered, and it is this interaction which is more important, and it is lower than the earlier energy gap. Since the energy gap is lower, extended perturbation, extended interaction would favor the reaction and would definitely speed up the process. Therefore, if I substitute a diene with an electron donating group, this HOMO goes up, HOMO-LUMO energy gap decreases, this HOMO goes up, HOMO-LUMO energy gap decreases, reaction intensifies or speeds up. Conversely, if I substitute the diene with an electron withdrawing group, this LUMO comes down, this HOMO comes down, similarly LUMO will also come down. If this LUMO comes down, this energy gap decreases. Now if this energy gap decreases, then this interaction is more important, and hence again reaction speeds up. Therefore, if I substitute diene either with electron donating or with electron withdrawing group, reaction is speeding up. Similarly, if you look at the Diophyte, substitute an electron donating group onto Diophyte, HOMO is raised, LUMO is raised. If HOMO is raised, this HOMO-LUMO interaction, that is HOMO of the Diophyte with LUMO of the diene's energy gap is smaller now. If it is smaller, reaction will speed up. Conversely, if you substitute it with an electron withdrawing group, HOMO goes down, LUMO goes down. If this LUMO goes down, this interaction is now important and reaction will be speeded up because the energy gap is reduced. Therefore, considering a type 2 reaction, any substitution, whether electron donating or electron withdrawing, onto any system, whether diene or Diophyte, tends to increase the reaction system. And if I look at type 3 category, I substitute a type 3 category. If you can now visualize yourself, type 3 is one in which HOMO of the Diophyte and LUMO of the diene is an important contribution. So any substitution that will raise HOMO of the Diophyte up, that is electron donating substitute on the Diophyte, electron donating substitute on Diophyte speeds up, electron withdrawing slows it down, and similarly onto diene, electron donating would slow down and electron withdrawing will speed up. To see this with the help of a figure, I can explain this thing, or we can explain this easily. This is the important interaction. If you substitute Diophyte with an electron donating group, HOMO is raised, energy gap lower, reaction speeds up. If you substitute Diophyte with electron withdrawing group, HOMO goes down, energy gap increases, reaction slows down. Conversely, if you substitute this with an electron donating group, HOMO goes up, LUMO goes up. If LUMO goes up, the energy gap increases, and if the energy gap increases, then in this case, this reaction slows down. Conversely, if you substitute diene with electron withdrawing group, LUMO goes down. If LUMO goes down, the energy gap decreases, and the reaction speeds up. Therefore, the speed of the reaction would be controlled on the basis of the type of cyclonation reactions we are discussing. At this stage of time, I'd be safely saying that if I'm discussing any system in which there is all carbon diene and an all carbon Diophyte, that means if we're simply talking about, let's say, a butadiene and methane, under these conditions, the normal Diels-Alder reactions is what we are talking about. That is, the HOMO of the diene is always at higher energy than the HOMO of the Diophyte. This is the type 1 category. Now let's add on to something else here. If I keep on substituting any system, either a diene or a Diophyte, let's say if I do successive substitution of an electron withdrawing group onto a diene, it reduces its energy level and brings it closer to energy levels of to the HOMO of the dienophile. Here I'm talking about, let's say, normal Diels-Alder cyclodation reaction. What I'm saying is, let's say this is my normal Diels-Alder cyclodation reaction picture. You substitute this diene with electron donate with electron withdrawing group. Energy level will decrease. Keep on bringing it down in terms of energy level by substituting electron withdrawing group. A stage will come when this HOMO of the diene will be close to the HOMO of the dienophile. That means if you successively substitute a diene with electron withdrawing groups, a stage will come, or a near stage will come, when HOMO of the diene and HOMO of the dienophile will be having similar energy. That means this is a point where we are transiting from type 1 category to the type 2 category. But normally speaking, or generally speaking, this does not happen. Generally speaking, electron withdrawing substitution does never bring down the energy level of HOMO of the diene below the energy level of HOMO of the dienophile. Therefore, simply by substituting diene with electron withdrawing groups would never pull down the HOMO of the diene lower in energy as compared to HOMO of the dienophile. Hence, the substitution patterns will not alter the course of the reaction. That would mean that this reaction would be 1. Therefore, nuclear substitutions will not change the type of a cyclodation reaction. It will not take a cyclodation reaction from type 1 to type 2 category or from type 2 to type 3 category. And for that to happen, if we substitute the carbons of the diene with an electronegative atom, let's say if I'm talking about a simple butadiene and then replace one carbon or more than one carbon with nitrogens, then what will it do? Replacing the carbon atoms with the more electronegative atoms like nitrogen or oxygen lowers the energy of the diene considerably, making it transit from type 1 to type 2 and finally to type 3, and where HOMO of the diene falls below the HOMO of the dienophile. Now, if the transition has to occur from type 1 to type 2 and conversely and then to type 3, then probably it is the atomic substitutions of the diene and the dienophile that will really change the course of the reaction, because once you substitute diene with any substituting group, this will not change the type of a Diels-Alder cyclonation reaction. However, if you change the atoms of the carbon atoms of the diene or a dienophile with some kind of electronegative atoms, then probably its HOMO falls down considerably and making it shift from type 1 to type 2, and if more substitution is there, it falls down to the even below the HOMO of the dienophile, shifting it to type 3 category. Now, on the basis of this, we have divided 3 classes of, let's say, dipoles. As you can see, 1,3 dipolar cyclodation reactions we have very recently done. 1,3 dipolar cyclodation reactions are a reaction between a 1,3 dipole, which is actually a 4-pi electron contributing system, and a dipolarophile, which is a 2-pi electron contributing system. Let's say that 1,3 dipole, which is a 4-pi electron contributing system, if it is an all carbon system, it falls under type 1 category. That is, the HOMO of the diene is higher in energy than HOMO of the dienophile. Similarly, substituting it with one nitrogen atom lowers its energy. Substituting it with 2 nitrogen, if this was the energy axis, let's say, if this was the energy axis, substituting one nitrogen atom lowers its energy, substituting it with 2 nitrogen atom further lowers its energy. If you substitute it with 2 nitrogen atoms, it lowers its energy. Substituting nitrogen and substituting carbon with oxygen lowers its energy more, and substituting all carbons with nitrogen makes it shift from type 1 to type 2 category. And finally, if you have oxygen substitutions, for example, in the case of one oxygen or all 3 oxygens are there, then the HOMO of the diene falls below the HOMO of dienophile. That is, in this particular case, it is the HOMO of the dienophile probably which is higher in energy than the HOMO of the 1,3 dipole, which therefore shifts it to the type 3 category. Now let's try to explain the facts using some examples. For example, we are studying a reaction between phenylazide as 1,3 dipole, and then we have to take a dipolarophile. Dipolarophile, we have taken 3 examples here. One is this one, in which a double bond is substituted by this pyrrolidine nucleus. One is a simple cyclohexene system, another one is a methyl acrylate system. Here, this double bond is substituted by nitrogen atom which has a lone pair. Therefore, we are talking about a group which is electron donating in nature. Here, this is a double bond which is substituted by hydrogens and carbon here. Let's say this system does not have any substitution. And finally, I have a double bond which is substituted by a carboxymethyl group, which is of course electron withdrawing in nature. So electron donating group, electron withdrawing group, and let's say this is no group. The result would be there will be a there will be a 4 plus 2 cycloaddition reaction between 1,3 dipole and the double bond of either this system or this system, resulting in the formation of this 5-membered ring, as we have studied in the case of 1,3 dipole cycloaddition reactions. If you see the result, if we talk about the rate constant of this reaction, probably in this particular case, the value of K using this double bond is, let's say, 1. If an electron donating group is substituted, the value increases. If electron withdrawing group substituted, again the value increases. That means any substitution, either it is electron donating or electron withdrawing, is actually intensifying or increasing the speed of the reaction, which makes us believe that the reaction of phenyl azides or azides fall under type 2 category. Therefore, this is a type 2 kind of Diels-Alder cyclonation reaction. Let's consider one more case. Let's consider the reaction of ozone O3 with the dipolarophile. I now know from my information of 1,3 dipoles that ozones fall under type 3 category. Now let's see and check the results. If I react ozone with the dipolarophile, I've taken different dipolarophiles here. I've taken a simple ethene. I've taken an ethene which is substituted by one methyl group. I've taken an ethene which is substituted by two methyl substitutions. Therefore, from going from here to here, I'm increasing the methyl substitutions, and I know methyl groups are electron donating groups through inductive effect. Therefore, from here to here, one electron donor group is substituted, and from here to here, two electron donor groups are substituted. That means onto the dianophile or the dipolarophile, we are substituting electron donating groups. Now, if it is a type 3 category, as we know, HOMO of the dipolarophile is lower in energy than HOMO of the dipole is lower in energy than HOMO of the dipolarophile. Therefore, the important interaction is the HOMO of the dipolarophile with the LUMO of the dipole. You substitute dipolarophile with electron donating group, it will raise its HOMO, lower the energy gap between the HOMO of the dipolarophile and LUMO of the dipole. As the result of it, the electron donation or donating group should intensify the reaction. With no substitution, the rate constant's value is 1. With a single methyl substitution, the rate constant increases. With two methyl substitutions, rate constant further increases, which goes to show that increasing electron donating substituents tends to raise the HOMO of dipolarophile, making the energy gap between the HOMO of the dipolarophile, LUMO of the dipole smaller. As a result, this is a type 3 category which we are discussing in this particular case. Okay, finally, we'll talk about the last example here regarding the rates of cycloaddition reaction. Let's say we're considering a reaction between this tetrazine molecule with, let's say, substituted ethene. Now, once this reacts with this, it forms a diazine molecule and nitrogen is extruded out. If you look at or consider this case, this reaction is something like this portion contributes as a 4 pi electrons and this portion contributes as a 2 pi electron. And how this reacts? First of all, it's a 4 plus 2 cycloaddition between these two components, and once it is done, then nitrogen probably extrudes out from the system, giving this diazine molecule as this one. Now, as you can see, the substitution of carbons here, if this was an all carbon system, then probably it would have followed a type 1 category. But substituting the all carbon systems with nitrogen atoms, probably what a nitrogen atom or electronegative atom does is it withdraws electrons from the system. If it withdraws electrons from a system like an electron withdrawing group, it would reduce the energy of the HOMO of the diene. Therefore, substitution of carbons of tetrazine with nitrogen atom, and along with this you substitute it with electron withdrawing group. So you are adding two effects. One, you are substituting the carbon atoms, or you are replacing the carbon atoms with electronegative nitrogen atom, which will lower the energy of the HOMO of the diene, and further you substitute that diene moiety with the carboxymethyl electron withdrawing substituents. It will further lower its energy, and since it will further lower its energy, probably now under this substitution and the replacement of carbon by nitrogen atoms, the reaction would probably move from the type 1 category, going from type 1 to type 2 and finally to the type 3 category. And also, if you increase electron donating substituents on the dipolarophile, this raises its energy level. Hence, one can effect or feel that there is a gradual change from type 1 to type 3, That is, as you keep on substituting carbons with nitrogen atoms, as you keep on substituting the diene with electron withdrawing groups, what will happen? Its HOMO will go down, 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 and a stage will come. It will shift from type 1 to type 2 and finally to type 3 category. And once it is shifted to type 3 category, it is then the HOMO of the HOMO of the dienophile and LUMO of the diene, which is more important contribution. And hence, under those conditions, if I substitute the dienophile with an electron donating group, the reaction tends to increase. The reaction speed tends to increase. Therefore, the reaction changes from type 1 to type 3 category, in which the more important or the more contributing interactions are HOMO of the dienophile with LUMO of the diene. That is, we are talking about the type 3 category here. So this is something regarding the rates of cycloaddition reactions. In our subsequent class, I think we are through with the third phases, cycloaddition reactions. In the subsequent classes, we'll talk first of all about the very important Cope and Claisen rearrangement. Thank you so much.